Make any drug good, or each drug still has its own effects. So, this is an analysis, it's called home, and there are 4 compartments. This compartment is the least damaged compartment, control suite compartment. This is the most damaged compartment, you can see. So there are a couple of drugs, like laminectomy. There are a couple of drugs, they are in this compartment. Whereas the other nanowire compartments are untreated, they are in this compartment. But some of the drugs are in between. So that suggests that nanowire alone is not able to make any bad drug to good drug. The drug must be good. Then if you deliver with nanomaterials, it can be better. So that is an example. I cannot tell the name of the drugs because these are still confidential. But you can see, you choose the best drug, and you can see the effect here that these myelin and also the ventral horn is much well protected as compared to the untreated group by this nanowire drug called AP713. In last 5 or 10 minutes, I will show you our recent experiments with Alzheimer model. So, I need not describe that how Alzheimer was done. This is a German physicist who took this human case in 1902 and found a entirely new type of disease named Alzheimer, on the name of God. Pathological picture will tell the difference between the brain. This is the Alzheimer brain and this is the normal. You can see why also. There are lots of theory in Alzheimer related to blood-brain barrier. Some people believe that blood-brain barrier is not expelling the amyloid beta peptide. But one should not forget, and that is the reason when we presented this paper in this year, San Diego, 9th clinical trial of Alzheimer's disease, people appreciate it. In our plasma, blood plasma, we have amyloid. In normal brain, also we have amyloid, but that does not give us that disease. So the point is that when this blood-brain barrier is leaky, amyloid beta peptide goes into the brain, also goes into the CSF. That is another way around is also that when it is going in the brain or CSF, the brain will try to expel it. But that function is also deteriorated. That is called brain-blood barrier. So this cartoon will only tell that endothelial cell is very, very important apart from neurons and glial cells. Now the point is that what we are doing for advanced treatment or therapy. As you can see, other people have shown that even stem cells can be nanowired and they live longer and produce better effects. This is an example. So this was when we had first used nanowire delivery of cerebrolizing in 2013 together with Professor Morassani in treating neuropathic pain. They found that that technology was 20% top. That award went to us, but my wife has even 15% top technology. So this was the innovation spotlight on cerebrolizing for treatment of neuropathic pain. So the point is that we have used 2 different models. One is mouse knockout mice model of Alzheimer's disease, and here you can see that we have measured amyloid beta in CSF, and you can see here that in this mice it is very high. When we have given cerebrolizing, it is reduced, but nanowire cerebrolizing did the best result. The same thing happened with tau, because you know that the phosphorylation of tau is also dangerous produced by amyloid beta peptide interaction. And here you can see the same thing. Nanowire cerebrolizing did the best as compared to the other conditions. Then we went to study microscopy. And here you can see amyloid beta diffusion induced brain pathology. That is our another model when this amyloid beta peptide 1 to 40, not 42, because 42 is very toxic. Animals will die. So 42 was infused for 4 weeks, and this is the leakage of albumin in the top panel, also the activation of astrocytes and the neuronal damages. When we have injected nanovirus cerebralizing, you can see albumin is less, astrocyte is not activated that much, and neurons look much normal. Looking at electron microscopy, because basically I am converted from neurophysiology to neuropathologist, so I believe everything what I can see. So these are the example I showed you, this myelin vesiculation, this amyloid beta peptide infusion, nanovirus cerebralizing, and cerebralizing alone. This part is much better. Then question is, can we combine? And this is our research that is claimed by many around the world, that we are combining different kinds of things. So we have used here nanowired mesenchymal stem cells here, and this is the same thing with amyloid beta infusion, and we have given this amyloid beta infusion after carotid brain injury, because brain injury, hypothermia, many things can aggravate. So in this situation, this is the nanowired cerebralizing alone, this is nanowired mesenchymal stem cell alone, and this is the combination. This combination gives the best result. Then we are working together with Sir Harry Grotto. He has special small molecules, small peptides, only 2 amino acids. And he thinks that these 2 amino acids could be much better therapeutic tool rather than 14 or 30. So we have some of his peptides, dipeptides. And the last idea is that in this talk, that we also compare PLGA level, because these are soft nanoparticles and drugs can be incorporated. So this is the part we did with, together with our Italian friend, and this is the PLGA loaded cerebralizing. What you can see that it is very stable and long lasting, gradually increasing the dose in plasma. This is also, you can see that it's great collaboration with Sir Sharma. I will show you these 2 pictures. This is the leakage of carbon barrier in amyloid beta peptide infusion. This is titanium nanowire and this is PLGA. Both are quite effective, but at the same scale, you can see that nanowire has better effect than the PLGA level, although both are good. Now these are the risks that we should work around. And for example, the another thing we are taking, as Professor Sharma mentioned, that we are working with national issue of drug abuse. The drug abuse, for example, methamphetamine is quite common, and some of you might be knowing that when Hitler wanted to win all over the world, he gave his soldiers methamphetamine. And then they feel that I can fight the whole world, I am so big, and they ruthlessly fought. These are German chronicle history, and I'm not sure that at the moment some countries are still trying, but these are the tricks people are doing. So this we are working in, and why we have problems that the animal and process clinical experiment, these are another aspect. So Dr. Shelley, he got Nobel Prize in Physiology and Medicine in 1977. He is still working in Miami. We are greatly impressed with his character. 3 or 4 papers every day he sends to journals to publish. So we are using different CRF fragments because on which he got Nobel Prize, and trying to level with nanomaterials. And finally, I will conclude because I am coming from University of Basque Country. So I will show some of the examples. They are working on how enriched environment itself can produce better results because of release of BDNF or something like that. And so this was the thesis in Parkinson's disease, and you can see that this is the MPPP treated Parkinson model. And this girl is Asia. She is working on another aspect of delivery of nanoparticles. So we have Kitinet nanospheres. These are hollow, and the cerebralizing was put inside. And you can see that it's gradually releasing the component. So this technology was tried by one of the students of Professor Jose Vicente vast country, and you can see that what they found, that this cerebralizing in this mode of delivery is much more better, and when it is combined with enriched environment, it is also doing great. You can see there are different things. This is the cerebralizing in all aspects of Parkinson's disease. So, and this was a thesis defended by one of a student, and his student Catalina, and Russell Andrews was the main examiner. He was very impressed. And finally, you can see that it's very difficult to work on these costly experiments without the involvement of government. He is a good person. He was 10 years Swedish Prime Minister, and probably at the end, high altitude reduced pregnant. This is the recent part that we have added together with US military, and you can see that these are the mountains, top mountains, in Napoca mountain in Afghanistan, more than 5,000 meters. And you can see here that the adverse effect is well known. We have used even heredity in a model, animal model, making in the laboratory. And I can only tell that even cerebralizing is doing good. We have some data. At the moment I can't show you because I don't have any permission to do that. So at the end, this nanomedicine is very good for that, and I will not take a long time. So what we are working, the comorbidity factors, that is the discovery of Professor Morisani, because he suggested the idea that we should do different comorbidity factors, not restricted only to one aspect, and that we are doing here. There are several organizations that support us and different people. And I stop here and Professor Agnesty. Thank you very much.
So thank you very much to Harry for this kind and excellent presentation. Very informative overview regarding the latest developments in basic research dedicated to brain protection and discovery. We are very happy because we have coined some important I'd say concepts, and particularly the concepts of comorbidities in animal models is one of our priorities of our group. At the beginning, smaller and then larger group, because everybody embraced this idea. So we have published in 2007 in New York Annals, and
yes, that's what you see.
it was a very cited paper in this very prestigious journal. We have published for the first time the idea that basic research, let's say, developed in a more relevant animal model would be a better added value than the classic experiments performed in healthy animals. So at that time we started with hypertension. Then we added the second comorbidity, which was diabetes, very important. And at the end we put the third important, non-specific, stressful agent, which is hyperthermia, and as we know very well. Then we have added step by step many other combinations of conditions in one animal. So you can imagine that, for example, a research generated by a healthy animal model in stroke, for example, with whatever model, we'll say artery, four vessel occlusion, whatever we'll use, at the end we'll generate some results based on healthy animal, and sometimes even we are forced by these rules to give anesthesia to animals.
Sure.
So we have absolutely totally different data coming from this model. So now, let's switch our attention to the more relevant animal model. Some an old rat with hypertension, diabetes, and whatever comorbidities. And also, we are not living in a clean world, as we have mentioned, and then dust, whatever, everything will contribute to a more real model. And then if you apply any kind of intervention, pharmacological, non-pharmacological, then you will get better results. And more, I would say, more reasonable results to be then incorporated in the concept of translational medicine. Because how can we translate, only this automatic narrow-minded knowledge? So this was one of our breakthroughs in the science in this respect. So I think this is very nicely going on. The second important message was dedicated to this fantastic new technotronic era and the nanotechnologies, and all our collaborators are doing great in this respect. I remember clearly, as in now, the 2008 meeting in Warsaw, when we met together, and the double Nobel Prize friend was who worked in this, rewiring of the brain in the capillary with self-polymerizing carbon fibers.
Yes.
So that was a fascinating model. So to reconnect different areas in the brain based on the still healthy vasculature, but introducing in one capillary up to 700, 800, and maybe 1,000 small wires, rewiring via vascular. So fascinating problem. So this is the nanotechnology was the very important message then. Another important aspect, it was the real better understanding of the role. So this was actually in the background of everything was blood-brain barrier. How blood-brain barrier will play in different circumstances. So I think this is, I would say, more or less, of course, we have many other projects, and particularly drug of abuse. It's extremely important, and we are very much looking for this data. So I think understanding all those aspects in a better way, and particularly understanding the real role of comorbidities and how an intervention will be better or effective or less effective in a real model, that will be very nice. Because we have demonstrated that the more comorbidities we have, the less relevant it's an intervention with one single molecule. So in a real patient, if they are young, and some of them I'm sure they will embrace research in the future, and they should know. The real life, it's very complicated. We have many drivers in pathogenesis. So lab should come closer to the real world. And this is our endeavor, to bring lab developments closer to the real world, to the real world pathogenesis. So I think in this respect, Professor Sharma and our humble contribution, we are many groups, but I think what we are doing, especially related to comorbidities, I'm very much excited, and we'll commit ourselves to further development in the best way.
Thank you. This was your idea. You started this work in this way, and now it has really acclaimed in many parts of the world.
So now, what I believe is that these young, nice fellows will have interesting and challenging questions for us. Yeah. So if you have if you feel that you'd like to address any question, please do so. Because they are delicious. You have to understand. But the curiosity may generate some wild thoughts. There is no wrong question, only
Yes.
Tell us, because we're using these titanium nanoparticles, are the concentrations of this titanium oxide high enough to produce already we could observe any adverse effects? First question. And the second question, because in the first slide you mentioned the role of hypothermia and lack of sleep and so on, so oxidative stress on the degree of BBB leakage. Can you explain further why did for example, the studies or the trials applying hypothermia
Well, the first question, it is mostly asked that what titanium nanowires are doing, okay, and whether they have any adverse effect on the brain. The first point is that these titanium wires are very tiny and they are innocuous. For example, up to 6 months or 2 years, as the literature says, because in Arkansas they are using this titanium nanowire after knee operation to have faster bone regeneration and healing. And in this case, there are lots of titanium wires were implanted after the knee operation, and the patients are doing fine for at least 6 to 10 years. So this is one thing. Then the point is that we are using titanium nanowire is very small dose, and obviously when they release the drug, they are still in the brain. That's very important. And the idea is we have just published a review together with Professor Murashano this year in CNS Central Nervous System Drug Target, that these titanium nanowires are less than, in the diameter, 0.5 micrometer or something like that. They can penetrate the cell membrane without damaging this, and they can enter into the brain and release the drugs. They are still there. In our hand, we have also used only titanium nanowire in the same doses that is delivering the drug. And up to 6 weeks, we don't see any adverse reaction. I did not show the data. So what we feel that obviously in this time, short period of time, they are not damaging the brain adversely up to some extent. The next question is that why hypothermia has increased or?
Hypothermia, failed to demonstrate protection.
Okay. This is very good question. And we have addressed this question by publishing a paper in Neuroscience in 2009. If you cool the brain, here is the changing. People say that if you cool the brain, it is protected. Okay? That's the stroke or many other cases. But the point is that in those circumstances, I believe the cooling is very deep. Okay? But here is 5 degrees Celsius. It is not 5 degrees Celsius is the environment, not the body temperature. Body temperature was 32 or 31. Okay? And I can give you another example. We have published the paper in 1991 when we have subjected the animals to force swim in the water of 34 degrees Celsius. After 30 minutes, their core body temperature was 31 degrees Celsius, but they are showing opening of the blood vessel. So the hypothermia itself is not a guarantee because this is also a stress. And in this neuroscience paper, we have shown that leakage of albumin, heat shock protein expression in hypothermia, that was 30 degrees Celsius, artificial cooling of anesthetized animals. So hypothermia is also a stress, releases so many factors, and therefore it is not able to protect the barrier. And this is also occurring in our soldiers when they are working in Afghanistan. They have many problems when they get injured, although they are really in frozen condition. Okay? Thanks for asking.
Is cold.
Yes.
So to make, this is excellent. Just to add a bit, because I'm sure that as neurologists would like to understand better, particularly in relationship with these nanoparticles. So the nanoparticles, when passing the blood-brain barrier, that is the charming fact, because let's say the capacity to penetrate without damage is the privilege of some types of neuroparticles, and these are titanium nanoparticles. But the same size of particle, different particles, like for example the copper, even silver sometimes, they will be damaged.
Yes.
So the nature of the particle and the size is extremely important. That once reaching the other side of the blood-brain barrier, after the releasing of the contact, then nothing bad will happen, because it looks like this titanium has a very special property of not disturbing the biological systems. And the neurovascular unit, that actually this is the functional and structural unit of the brain. The neurovascular unit will stay silent, will not react. And the remaining particles in the brain will be slowly cleared by the microglia, slowly then. Yeah? So we shouldn't use every day, but if we use in the acute setting, an intervention of that type, anyhow, the magnitude of the effect will be higher, and then without any disturbances, it will be a silent clearance of the nanoparticles of titanium nanoparticles. This is not the case with other particles. The other particles that will damage from the very beginning, particularly the occludine, the molecules that are regulating the permeability. So that would be, this is the nature of the nanoparticle and the size. It's extremely important. Of course, if you increase the size of titanium, then you have problems. But from that size and that particular thing, it looks very, very promising. So that is the background. Yeah? We don't know if you overload the brain with, I would say, a very high quantity, this particle, what will happen. But up to a normal, up to a certain level, it's absolutely not.
Yeah, German research paper showed that even injecting 50 milligram per kilogram titanium intraperitoneally in mice for 2 years does not produce any damage to the brain. And what we have shown that you use same size and same dose of silver, copper, and aluminium. Aluminium is the least damaging to the barrier as compared to these two. So both the inherent properties of the nanoparticles and their size both plays important role. So we have to choose specific nanoparticles.